So continuing on our discussion of uniform circular motion, we're now going to look at the concept of centripetal acceleration. Again, acceleration means it's kinematics. It's a change in motion, a change in velocity. Now, velocity changes in two ways. Velocity can change via the speed, and that's how we normally think of acceleration. We hit the gas pedal, we speed up. We hit the brake, we decelerate. Right? Acceleration, both our cases are acceleration, a change in the speed. But direction is also important. If an object changes direction, it's being accelerated, even if the speed isn't changing. That's critical for uniform circular motion. In uniform circular motion, an object's direction is constantly changing, but its speed is not. Again, imagine a rock on a rope being swung around your head at constant speed, or the International Space Station orbiting the Earth, or the Earth orbiting the Sun. Well, that's an approximation. Or a circular track where a car is constantly going around in a circle. Or you just going around a curve in your car. Even though you have the cruise set at 65 miles an hour on the highway, if you go around a curve, you're being accelerated because your direction of motion is changing. So, centripetal acceleration is a special class of acceleration. It's acceleration that causes uniform circular motion. It is centripetal means center seeking. Centri meaning center, petal meaning seeking. And think of it like a flower petal. If you've ever seen sunflowers, they turn to face the sun, they seek the sun. That's what a petal basically means. So center seeking acceleration. So A sub C is a class of acceleration that causes uniform circular motion. Now, accelerations, we know, are caused by forces. So what force causes centripetal acceleration? It's a centripetal force. Okay, but what is a centripetal force? I know friction makes sense. I know tension, I can pull on something or push something, right? I can shove someone over. Gravity is a force that makes sense, right? Weight is a concept I understand. What is this centripetal force which causes a centripetal acceleration? It's not a force, a specific force at all. It's a class of forces. Any force that acts to cause uniform circular motion is a centripetal force. So centripetal forces can be friction. In the case of a NASCAR driver driving around in a circle, the friction of the tires on the road keep that car moving in a circle. If the ramp, if it's a flat track, and let's say it's frictionless, all right, imagine it being super, super icy, you can't drive in a circle. If you've ever been on an icy road, and of course most of you from Wisconsin probably have, you driving in a straight line on a highway, there's a curve coming up, but the road's icy. What happens? You turn the wheel, but nothing happens. Your car continues to go straight off the road. So friction can be a centripetal force. Not all friction is, like pushing a box in a straight line, the friction pushing back on you isn't a centripetal force. But car tires, for example, car tires on the road is an example of a centripetal frictional force. Gravity, right? This dropping straight down, not centripetal. This is not uniform circular motion. But the moon going around the Earth is. The astronauts in the space station going around the Earth, that is a uniform circular motion caused by gravity. Tension. You take a rock, tie a rope around it, and swing it around your head. That's uniform circular motion caused by the tension in the rope. Cut the rope, the rock isn't going to keep on orbiting your head. It's going to fly off in a straight line. So I have over here just a discussion of what do I mean by centripetal acceleration. Well, it's acceleration that has to point to the center of motion. So if I have here a circle of radius r, imagine the Earth is at the center and this is the moon going around, or the sun at the center and the Earth going around, or whatever example you want to use. At this point up here, I have the velocity going to the right. The magnitude of this line gives the speed. The direction, of course, gives the direction of motion. So that's velocity. The acceleration is pointing to the middle. Now, at some time later, the object is here. The velocity now is pointing a little bit down and to the left. I'm not quite at the bottom of the circle yet. The acceleration is still pointing to the middle. Sometime later, the object's over here. Velocity now is pointing a little bit up and to the left. Acceleration is pointing to the middle. So the acceleration at all times is perpendicular to the velocity. That's important for uniform circular motion, because if any part of this acceleration vector is in the direction of the velocity, if the acceleration is in the direction of the velocity, the object speeds up. If it's a little bit against the direction, if it's against the direction of the velocity is going in this direction, the acceleration has some component in that direction, the object will slow down. The speed will change. However, if the acceleration is perpendicular to the velocity, the only thing that changes for the velocity is the direction. The speed doesn't change, the direction does. And your book, I think, goes through a derivation of this, which I'm skipping over. The relationship between the acceleration, the speed, and the size of the circle, the radius of the circle or orbit, is given by this equation here. So this is the equation for centripetal acceleration. Centripetal acceleration depends upon, is equal to the speed squared divided by the radius. So we can actually use this to calculate some interesting things. I could use this to find out how fast are the astronauts actually orbiting the Earth. I know the radius of the astronauts from the center of the Earth. I know the acceleration is gravity, so it's not quite 9.8 up in space, it's a little bit less, but we can approximate, and I can find out what their speed is. If I know what the gravitational force is between the Earth and the Moon, I can use the Moon's orbit radius from the Earth and figure out how fast the Moon is moving. Or I can do this with, find out how fast the Earth is moving about the Sun, and so on. Now this is an acceleration. Accelerations are caused by forces. I talked before about how centripetal accelerations are caused by centripetal forces, center-seeking forces. Since the acceleration is always to the center, that means, and F equals ma, mass is a scalar, that means the force is always in the direction of the acceleration. The net force is always in the direction of the acceleration. In this case, the net force is always pointing to the center of motion for uniform circular motion. Force is mass times acceleration. Well, here's mass. Acceleration, centripetal acceleration, I know is v squared over r, so I can substitute that in here. So the centripetal force is mass times v, the speed squared, over r. This relationship we'll use in a bit to talk about, to derive a famous set of equations called Kepler's laws. So we can use this concept of centripetal force and centripetal acceleration to look at a concept of road building called a banked curve. Now, banked curves exist on regular highway roads. They exist, interstate roads, of course. They certainly exist in racing events. NASCAR can have very steep banked hills. And a very popular way of doing banked curves is Olympics, the luge or the skeleton, the winter sports where a sled is sent down at a very rapid pace, very fast pace down a course. Well, ice is very low friction. So how do you get the sled to turn? Or if you're the skeleton, right? If you're just the person, arms at your side, flying down this very narrow, ice-covered path, how do you curve? Well, curves are done through banking. And the concept of banking allows us to accelerate objects around curves. So, for example, let's look at luge. Looks like a little spaceship here, but it's supposed to be a sled with skis and the head of a person sticking out. So how do we get this person to turn, imagine them going into the board, how do we get them to turn to the left? If this is completely flat, they wouldn't. They keep on going in a straight line. In order to accelerate, i.e. change your velocity, change the direction you're moving, you need to accelerate. So by banking, by making this a curve that's down to the left and up to the right, what happens is the weight of the sled and the occupants is still downward, right? It's still in the negative y direction. However, the normal force now, which is perpendicular to the surface, tips up into the left. The normal force does not always balance the weight. Only does that if there are no other forces on the object in the y direction and if the platform is horizontal or flat. Here it's not flat. So the normal force pushes up and to the left. So let's look at the free body diagram, and I have here this angle here theta, because that's of course important, because the steeper theta is, the more the normal force points to the left. Here's the free body diagram. Move around. Here's the free body diagram. So the normal force is pointing up and to the left. The angle from the vertical is equal to theta. And hopefully you have the geometry ability to prove that this theta is the same as that theta. One way to think about it is if this is flat, theta is 0, and the normal force would point straight up, so this theta would be 0. If this is 90 degrees, the normal force would be pointing to the left. This would be also 90 degrees. So we can use trigonometry to talk about the normal force. The normal force we break up into two components. There's the y component, which balances the weight of the object. And then there's the x component, which is pointing to the left. There's no other x component on this object. The weight is strictly in the y direction. Since there is no other x component on this object, that is a force that will accelerate the object. So looking at what we have here, the weight is balanced by the normal force in the y direction. The normal force in the y direction is equal to n sub y balances the weight. The normal force in the y direction, that's the cosine, right? This is a 90-degree angle here. This is the adjacent side, and is the hypotenuse for angle theta. So for the adjacent side, that's the cosine. So n times cosine theta is the weight. Those have to balance according to Newton's second law, because there is no acceleration in the y direction. There is acceleration in the x direction, though, so n sine theta, n sub x, is the opposite side of this triangle. So it's equal to, n sub x is equal to n times sine theta. That's the centripetal force. So, question would be, what is the ideal angle that this needs to be banked at in order for the object to accelerate around the curve in a frictionless case? Normally, on a flat road that curves, your tires provide the friction to push you around the corner. But on a slippery road, that wouldn't work. Or for the luge, or the skeleton, right, you don't have enough friction to push you around that corner. It's ice you're traveling on. So you have to tip this up at some angle, but what angle depends on a couple of different things. So we want to try to find out, how do we figure out the ideal banked angle in order to direct something around the corner. So we have two equations here. Both have n in it, the normal. Both have angle theta in it. One has the weight, and the other is the centripetal force. So what I'm going to do is I'm going to rearrange these equations. I'm going to solve them both for n and then set them equal to one another. So solving this first one for n, I divide both sides by cosine theta. So I get the weight over cosine theta, that's n. For the second one, I divide both sides by sine theta. So I get the centripetal force over sine theta, that's equal to n. So those are equal to each other. N disappears. We don't need to know what the normal force is in order to find out what the ideal angle is. That's good. Well, I have theta here twice, and I don't want theta twice. I just want to be able to solve for theta. So I'm going to get theta on one side and the other terms on the other. So I'm going to multiply both sides of this equation by sine theta. That brings the sine from the denominator over here to the numerator on the left-hand side. Divide both sides by the weight. That brings the weight down, and I end up with this equation. Sine theta over cosine theta is the centripetal force over the weight. Now I'm going to do some substitution. The first one is sine over cosine is tangent. So sine theta over cosine theta is tangent theta. That's, again, trigonometry. That's equal to the centripetal force from the previous discussion earlier in this video. We talked about that the centripetal force is mv squared over r. And the weight is m times g, the mass of the object times the acceleration due to gravity. So I plug all those in. Hey, there's an m on the top from the centripetal force. there's an m on the bottom from the weight, mass cancels. Well, that's kind of neat. That means our answer won't depend on the mass of the object. So a light skeleton person flying down the hill will be turned the same amount as a heavy skeleton person flying down the hill. Or a light NASCAR going around the corner will bank just as much as a heavier NASCAR. We can rearrange this equation, solve for theta, and the equation we end up getting, in the end, theta is equal to the inverse tangent of v squared over r times g. So the angle depends upon, again, tangent. So if you want the angle in degrees, make sure you're in degree mode when you do this equation. It depends on the speed. It depends on the radius for the turn, how quick the turn is. And it depends on g. Well, g is a constant on Earth, so if you're calculating this for the skeleton, then, you know, we're not doing the Olympics in the center of the Earth, so g stays 9.80 meters per second squared. This kind of makes sense that the embankment here, the angle depends on how quick the turn is, right? If this is a very, very large radius, it's a gradual curve, theta doesn't need to be very big. If this is a very, very small radius, it's a tight curve, then theta has to be much larger to get you around that corner, that fast corner. And then finally, it depends on the speed. In fact, the speed squared of the object moving. And if you do watch Olympic sports, like skeleton, for instance, you can actually kind of see that when you're watching the luge or skeleton. When they do hit those banked curves, the faster people go up higher on the banked curves. So you can kind of see which person, which group is actually faster because of how high they get as they bank around that curve. Because the faster people actually need a steeper angle, and of course the bank curves, you know, the angle depends on how high you are up on that curve. So the higher you get on that curve, the faster you were going. So this equation gives the ideal banking. Now, this is done. You can actually calculate what that would be for a car around a curved road. And it turns out the banking doesn't need to be very large. But this helps with cars traveling at high speeds. That's why interstates are banked when they go around, especially sharp corners, sharp turns, especially mountainous regions where you can't have a flat highway. Now, if roads are we could have roads completely flat throughout the entire US except for, you know, gradients, highs and lows as we go over mountains. But Nebraska, very flat land. We could have the sharp curves flat. And what that simply means is you're relying on the friction of your tires to get you around that corner. So if you lose grip, if it's slippery as an oil slick or ice, you're more likely to crash. With a banked curve, you're putting less pressure, less force on your tires. You're relying on your tires less. So even if this road were completely icy, your car would actually still, depending on the speed, your car would still go around the curve. So it's a nice safety feature on some highways.